Now, let us drift away from the solitary specks of light scattered across the infinite black velvet, away from the well-trodden paths of planets and moons, and journey deeper into the quiet, unseen realms of the cosmos. Imagine floating through that endless, silent ocean of space, where the distances are so vast they stretch the imagination thin. For much of this journey, the view remains the same: the sharp, distant pinpricks of stars against an overwhelming darkness. But eventually, in certain special corners of the universe, the pure black begins to soften. It might start subtly, a faint bismarck where the darkness seems less absolute, perhaps a hint of texture where before there was only void. As we draw closer, drawn by an unseen current, these textures resolve themselves into something extraordinary. Vast, luminous clouds unfurl before us, hanging like immense, watercolor paintings against the backdrop of space. These are the nebulae, the star nurseries, the gentle, embracing clouds of gas and dust where the story of stars truly begins. They are places of profound, quiet, and unimaginable scale, the soft, fertile grounds of the galaxy. Forget the sharp edges and solid forms we know on Earth. Nebulae are ethereal, diaphanous structures, woven from the most delicate threads imaginable. They stretch for light years, distances so immense that light itself, the fastest messenger in the universe, takes decades, centuries, even millennia, to cross from one edge to the other. Within their expanse, you could place not just one solar system like ours, but thousands upon thousands, and still have room to spare. Yet, despite their overwhelming size, they are incredibly diffuse, far more tenuous than the wispiest cloud in our own sky. If you could somehow cup a handful of a nebula in your hands, an impossible feat of course, you would likely hold only a few atoms of gas, perhaps a single, microscopic grain of dust. It is mostly emptiness, a scented void, a potential waiting to coalesce. These clouds are primarily composed of the simplest and most abundant elements in the universe, hydrogen and helium gas. Think of vast, invisible oceans of hydrogen, the primordial breath of creation, laced with a smaller amount of helium. But mixed within this transparency is something else, something crucial: dust. Not the dust bunnies under the bed, but microscopic grains, tinier than motes dancing in a sunbeam. These grains are composed of heavier elements: carbon, silicon, oxygen, iron, forged long ago in the hearts of earlier generations of stars and scattered back into space. This cosmic dust, fine as smoke, plays a vital role. It drifts amongst the gas, sometimes obscuring the light from stars behind it, creating dark lanes and intricate silhouettes within the glowing clouds. It's this dust that helps give nebulae their structure, their texture, their sense of depth. Visually, nebulae are among the most beautiful and awe-inspiring sights the universe has to offer. They come in a breathtaking variety of shapes and colors, painted by the light of stars nearby or embedded within them. Some glow with a soft, rosy pink light. This happens when energetic light from young, hot stars buried deep inside the cloud excites the surrounding hydrogen gas, causing it to emit its own characteristic reddish glow. These are called emission nebulae, and they often look like vast, blooming cosmic roses or intricate, fiery landscapes. Imagine the Orion Nebula, a famous stellar nursery relatively close to us, a turbulent cauldron of creation where brilliant new stars are illuminating the gas around them in stunning shades of pink, red, and violet. It's a place of active birth, yet viewed from afar, it possesses a serene, majestic beauty. Other nebulae don't generate their own light, but instead act like celestial mirrors. If a cloud of gas and dust happens to be near a bright star, but not close enough for the gas to be fully energized, the tiny dust grains within the cloud will scatter the starlight. Blue light scatters more effectively than red light, the same reason our own sky appears blue. And so, these reflection nebulae shimmer with a delicate, cool bluish hue. They often appear wispy and ghost-like, ethereal veils draped across the darkness, hinting at the stars hidden nearby whose light they borrow. Think of the Pleiades star cluster, where young, bright blue stars are still wrapped in the faint, bluish remnants of the nebula from which they formed, like jewels on pale blue velvet. And then there are the dark nebulae. These are clouds so dense with gas, and especially dust, that they completely block the light from stars located behind them. They don't glow or shimmer. Instead, they appear as holes or dark patches punched out of the starry background. They might look like winding rivers of blackness, or looming, shadowy figures against a brighter backdrop. Perhaps the most famous example is the Horsehead Nebula, a stunning silhouette of a knight's chess piece set against a glowing pink emission nebula. These dark clouds might seem empty or forbidding, but they are anything but. Within their deep, obscuring folds, the dust provides essential shielding, creating pockets of intense cold and darkness, where the process of starbirth can begin undisturbed. They are the quietest, most hidden corners of the nursery. Within all these types of nebulae, whether glowing, reflecting, or dark, the same gentle, fundamental process is underway. These vast, cool clouds are not static. They are slowly, patiently responding to the quiet insistence of gravity. Gravity, that universal force of attraction, works tirelessly over immense timescales. Even in these incredibly diffuse clouds, tiny fluctuations exist, areas where the gas and dust are just slightly denser than average. These minuscule seeds of density exert a slightly stronger gravitational pull than their surroundings. Imagine it like the gentlest of eddies forming in a vast, still pond. Over millions upon millions of years, these denser regions slowly begin to draw more material towards them. Wisps of hydrogen gas drift inwards, grains of dust spiral gently closer. It's not a sudden collapse, not a violent implosion, but rather a gradual gathering, an inexorable, slow-motion drift. The cloud begins to fragment, breaking down into smaller, denser clumps, each one a potential birthplace for a star or a group of stars. The dust plays a crucial role here too. As these clumps contract, the gas atoms within them bump into each other more often, which would normally cause them to heat up and push back against gravity's pull. But the dust grains act like tiny radiators. They absorb this heat energy and then re-radiate it away as infrared light, allowing the clump to stay cool and continue its slow, gentle collapse. The dust provides the shelter and the cooling mechanism necessary for gravity to win its patient game. Think of these nebulae, these cozy clouds of dust and gas, as the wombs of the galaxy. They are vast, protective environments, holding the raw materials and providing the right conditions for new stars to form. Within their soft, colorful folds, the universe is patiently assembling its next generation of lights. The process is unhurried, unfolding over timescales that dwarf human comprehension. Millions of years pass, as gravity gently shepherds the diffuse gas and dust into denser knots, the precursors to stars. It is a place of quiet potential, of beginnings, of the universe gathering its breath before igniting new suns. These star nurseries are not just beautiful astronomical objects, they are the serene, essential cradles where the life cycle of stars commences, hidden within the gentle embrace of cosmic clouds. From these quiet, dusty beginnings, the first sparks of stellar life will eventually ignite, but that is a story for the next part of our journey. For now, picture these immense, peaceful clouds, drifting silently through the dark, holding within them the promise of countless future stars. Within the vast, quiet expanse of the nebula, where cosmic dust motes drift like suspended thoughts and gases swirl in slow, ethereal dances, the patient work of gravity continues. Imagine focusing now, drifting closer, past the shimmering curtains of ionized hydrogen and through the cooler, darker lanes where the dust lies thickest. Here, within these denser regions, these knots of potential we spoke of, the universe takes its next quiet step. Gravity, that ever-present, gentle guide, begins to exert its subtle influence with more focused intent. It is not a sudden grasp, but a persistent, quiet invitation. Think of it as the gentlest of currents in an infinitely large, still ocean. Particles of gas, hydrogen atoms mostly, and tiny grains of dust, separated by vast distances within their clump, feel the faintest of tugs towards a common center. It's an attraction so weak initially that it seems almost insignificant, yet it is relentless. Over countless millennia, this whisper of gravity draws the material inwards. It's like watching mist slowly coalesce on a cool morning, the individual droplets invisible until they begin to gather, forming a denser patch, a focal point in the haze. The clump begins to contract, shrinking ever so slowly, pulling its scattered constituents closer together. The process is not chaotic, but ordered in its own unhurried way. As the particles drift closer, the clump doesn't just shrink uniformly like a deflating balloon. Instead, the material near the very center, where the gravitational pull is strongest, begins to accumulate more rapidly. A core starts to form, a denser heart within the collapsing cloud. It's the very beginning of structure, a concentration emerging from the diffuse haze. The outer parts of the clump feel this central pull too, and they begin a slow, spiraling journey inwards, raining down towards this growing heart. Remember how the dust grains acted as tiny radiators, cooling the cloud and allowing this collapse to begin? That crucial process continues, especially in the outer, less dense parts of the collapsing clump. Heat generated by the initial compression is efficiently radiated away into the coldness of space as infrared light, keeping these outer layers cool and allowing gravity to maintain its gentle hold, drawing ever more material inwards. But deep within that forming core, something begins to change. As more and more gas and dust accumulate at the center, the density increases dramatically. The particles are packed closer and closer together. Imagine the space between them shrinking, from vast emptiness to merely cosmic elbow room, and then tighter still. They bump into each other far more frequently now, jostling and colliding in the heart of the clump. Each collision, however small, converts the energy of motion, the energy gained from falling inwards under gravity's pull, into heat. At first, even here, the dust tries its best to radiate this warmth away, but the core is becoming opaque, shrouded by the sheer concentration of matter. The heat generated deep inside finds it harder and harder to escape. It's like pulling a thicker blanket around yourself on a cold night. Your own body heat starts to build up, trapped beneath the layers. The dust grains, once efficient radiators, are now caught within a thickening fog of gas, their infrared emissions struggling to find a clear path out. And so, the core begins ever so slowly to warm up. This is not the fierce heat of a burning fire, but a gentle, pervasive warmth spreading through the densest part of the clump. It's the warmth generated by relentless compression, the energy of gravitational collapse transforming into thermal energy. Picture rubbing your hands together very slowly, a subtle warmth builds. Here, countless trillions of particles falling inwards and pressing together create a similar effect, but on a cosmic scale. The temperature at the very center starts to climb, rising from the near absolute zero of interstellar space to tens, then hundreds, then thousands of degrees. This warming, dense core, still gathering mass from the surrounding cloud, is what astronomers call a protostar. It is not yet a true star. It hasn't ignited the nuclear fires that will eventually make it shine brightly. It is, instead, an embryonic star, a star in the making. It's hidden from view in visible light, completely cocooned within the thick layers of gas and dust that are still falling onto it. If you were looking with human eyes, you would see only the dark, opaque cloud. But if you could see an infrared light, the light of heat itself, you would detect a faint, warm glow emanating from deep within the darkness. This is the protostar, radiating away the heat of its own gravitational contraction. Imagine this protostar as something waking from a long, cold sleep. The nebula was its quiet, dreaming phase. Now, as gravity compresses its core, it begins to stir. The rising temperature is the first sign of this awakening, a slow return of warmth to limbs that have been cold for eons. It's a drowsy process, unfolding over hundreds of thousands of years. Material continues to rain down onto the protostar from the surrounding envelope, a gentle accretion that adds to its mass and squeezes the core ever tighter, causing it to grow warmer still. This infalling material doesn't just drop straight down. Because the original cloud likely had some tiny, almost imperceptible rotation, as the material falls inwards, it begins to spin faster, like an ice skater pulling their arms in. This causes some of the gas and dust to flatten into a swirling disk around the protostar's equator. Think of a slow whirlpool or eddy forming around a central point, a flattened structure of gas and dust orbiting the growing, warming heart. This disk, a natural consequence of the collapse, might one day form planets, but for now, It's part of the feeding process, channeling material towards the hungry protostar at its center. The protostar itself continues its slow evolution, hidden within its dusty cradle. It grows denser, hotter, its internal pressure steadily building in response to the relentless crush of gravity. It is a delicate balance, the inward pull of gravity versus the outward push of the accumulating heat and pressure. For now, gravity is still winning the overall battle, continuing to draw material inwards and increase the core's mass and temperature. This phase is a crucial gestation period. The protostar is gathering the mass and the heat it will need for the next, more dramatic stage of its life. This gentle warming, this slow gathering of mass and heat, is the tiny spark of our title. It's not the brilliant flash of ignition, but the first internal glow, the first sign that the immense potential energy stored within the nebula's gas is being converted into a new form. It's a promise of the light to come, hidden deep within the cosmic womb. The protostar is the universe gathering its strength, concentrating its resources, preparing for the moment when true stellar life will begin. It's a process steeped in patience, unfolding on timescales that make human lifetimes seem instantaneous. Millennia upon millennia pass as the protostar slowly contracts, warms, and grows, nestled deep within its nurturing cloud. It remains a secret held by the darkness, a warm heart beating faintly, waiting for the moment when its internal temperature and pressure reach the critical point needed to ignite the fires of nuclear fusion. Until then, it rests in this intermediate state, a star waking up, its first warmth, a gentle harbinger of the brilliant light it will one day pour into the cosmos. Picture it there, a warm ember glowing softly in the immense, quiet, dark, surrounded by its swirling disk and infalling shroud, patiently preparing for its stellar debut. And then, it happens. Not with a sudden roar, but perhaps more like the quiet, profound click of a universe-sized lock finding its key. Deep within the heart of the contracting cloud, where the pressure has become immense and the heat unbearable by any earthly standard, the threshold is crossed. 10 million degrees. A magical number, whispered in the language of physics. At this temperature, the tiny protons, the very hearts of hydrogen atoms, which have spent eons merely jostling and warming, now find themselves pushed together with such unimaginable force that they overcome their natural reluctance to touch. They fuse, they merge. In this instant, the star truly awakens. This is not the fleeting warmth of gravitational collapse anymore. This is something new, something self-sustaining. It is the birth of nuclear fire, a process of cosmic alchemy where hydrogen, the simplest and most abundant element, begins its long transformation into helium. 4 hydrogen nuclei, through a delicate, multi-step dance, eventually become one helium nucleus. And in this transformation, a tiny fraction of their combined mass simply vanishes. It doesn't disappear entirely, of course, but is converted into pure energy, released according to Einstein's famous cosmic equation. A photon of light springs forth, a tiny packet of radiant energy born from the fusion. Then, another, and another. A cascade begins, deep in the core. This newly released energy pushes outwards, a gentle but insistent pressure from the heart of the star. It's the star's first outward breath, powered by the nuclear furnace it has just ignited. And this outward push meets the relentless inward pull of gravity, the force that has been squeezing the star into existence. For long ages, gravity had the upper hand, compressing the protostar. But now, the outward pressure generated by the heat of fusion rises to meet it. A balance is struck, a celestial equilibrium is achieved. Imagine a perfect, silent standoff. Gravity pulls inwards, trying to crush the star further, while the energy released by fusion pushes outwards, trying to expand it. These two colossal forces find a point of exquisite balance, a state known as hydrostatic equilibrium. The star ceases to contract. It settles. It finds its size, its temperature, its brightness, and it holds them steady. It has entered the longest and most stable phase of its existence, the phase astronomers call the main sequence. This is the star's long, quiet adulthood, its serene and steady day. For a star like our own Sun, this period of stability is incredibly long, stretching across billions upon billions of years. It is a time of quiet consistency. Deep in the core, the fusion of hydrogen into helium continues at a remarkably constant rate. It's like a vast, slow-burning hearth, tended by the laws of physics themselves. The hydrogen fuel is consumed gradually, meticulously, ensuring a steady output of energy for an immense span of time. The star isn't frantically burning through its reserves, it is sipping its fuel, making it last. The energy born in the core doesn't instantly appear at the surface. Those photons, those tiny messengers of light created in the fusion furnace, begin a long and meandering journey outwards. They are absorbed by particles of matter, then re-emitted, absorbed again, re-emitted again, bouncing randomly this way and that within the star's incredibly dense interior. It's not a straight path, but a staggeringly complex random walk. A single photon created in the core might take tens of thousands, even hundreds of thousands, of years to finally reach the star's surface and escape into space. Think of that. The light warming your face on a sunny day began its journey from the sun's core long before human civilization even began. As the energy slowly percolates outwards, it travels through different layers within the star. Closest to the core is the radiative zone, where energy travels primarily as these wandering photons. Further out, the gas becomes cooler and denser, making it harder for photons to push through easily. Here, energy transport becomes dominated by convection. Great currents of hot plasma, like water boiling slowly in a pot, rise towards the surface, carrying their heat with them. They cool as they reach the surface, release their energy, and then sink back down to be heated again. This constant, slow, churning motion happens just beneath the visible surface, the photosphere. And it is from this photosphere that the light we see finally streams freely into the cosmos. It pours out in all directions, a continuous, unwavering flood of radiation. This is the star's steady shining, the gentle radiance that defines its main sequence life. It is a light that carries warmth and energy across vast distances. It bathes any planets that may orbit it in a consistent glow, providing the stable conditions that might, just might, allow life to emerge and evolve on worlds fortunate enough to reside within its habitable zone. Our sun is currently in the midst of its own long, calm day. It has been shining steadily in this manner for about 4.5 billion years, and it has enough hydrogen fuel left in its core to continue doing so for another 5 billion years, or perhaps even longer. It is middle-aged, settled, reliable. Its output varies only slightly, minor fluctuations over long cycles, but overall, it maintains an impressive constancy. It is the dependable anchor of our solar system. Imagine the star hanging there in the velvet blackness of space. Not a frantic, sputtering flame, but a serene, self-contained sphere of light. Its surface, while appearing calm from afar, might seethe with the tops of those convection currents, creating granular patterns and occasionally burping out flares or prominences, small variations on a theme of immense stability, but fundamentally, it remains in balance. The inward crush of gravity is perfectly held at bay by the outward pressure from the nuclear reactions humming deep within its core. This long main sequence phase is the quiet heart of stellar evolution. While the birth of a star is a dramatic gathering from dust and gas, and its eventual death can be spectacular, this intervening period is characterized by its profound steadiness. It is the time when the star simply is. It shines. It converts hydrogen to helium. It radiates energy. It holds its shape and size. It performs its cosmic duty with quiet diligence. Think of the sheer duration, billions of years, enough time for mountains to rise and fall on orbiting planets, for oceans to form and reshape continents, for life itself to potentially spark, evolve, and perhaps even contemplate the steady star that makes it all possible. The star is a constant presence, a celestial metronome marking out the slow passage of cosmic time. Its long, calm day provides the stability necessary for the intricate processes of planetary evolution and potentially biology to unfold. It is a piece born of immense power held in perfect check. The forces at play are unimaginable. Gravitational forces that could crush worlds, nuclear reactions releasing energy equivalent to billions of nuclear bombs every second. Yet, they are balanced so precisely that the result is not chaos, but calm. A shining, steady sphere, pouring out light and life-giving warmth, generation after generation, epoch after epoch. It is the universe demonstrating its capacity not just for explosive creation, but for enduring, patient radiance. This is the main sequence, the star, settled and serene, living out its long, luminous, and peaceful day. And so, this long, quiet day unfolds for countless stars across the vast, dark meadows of space. A time of balance, of steady shining, a peaceful middle age where the outward push of light holds the inward pull of gravity in a gentle, enduring embrace. But just as the trees in a forest are not all the same height, nor the flowers in a field all the same size, stars too are born with different beginnings. Different amounts of the cosmic dust and gas gathered close in their nursery clouds. Some gather just enough to flicker gently into life, while others pull in enormous amounts, becoming giants from their very first breath of fire. Our own sun, the warm heart of our solar system, is a rather average star in the grand scheme of things, neither particularly small nor exceptionally large. It sits comfortably in the middle ground. But look closer into the cosmic neighborhood, and you will find the differences are profound, leading these celestial siblings down very different roads, as their long lives eventually draw towards their twilight. It is here, in their inherent size, their birth weight determined billions of years ago, that their ultimate sleepy time story is decided. Two main paths diverge from this long, stable daytime, shaped entirely by how much stuff the star began with. Let us first imagine the little stars, those smaller and lighter than our sun, sometimes much smaller. These are the quiet ones, the truly patient members of the stellar family. Often, they glow with a softer, warmer light, perhaps a gentle orange or even a deep, ruby red, like cosmic embers tucked away in the darkness. Because they are less massive, the gravitational squeeze at their core is gentler. It's still powerful enough to ignite the nuclear fire, yes, but it doesn't demand the frantic, rapid burning we see in larger stars. These little stars are the universe's masters of conservation. They sip their fuel, the hydrogen stored deep within their hearts, incredibly slowly. Their main sequence, their calm and steady day, is therefore stretched out almost unimaginably. While a star like our Sun might shine steadily for 10 billion years, these smaller, dimmer stars can potentially keep their gentle glow alive for trillions of years. That's hundreds, even thousands of times longer than the current age of the universe itself. Think of them as the quietest neighbors on the cosmic street, their porch lights burning reliably, almost eternally, through the long, slow night of time. They watch generations of larger, brighter stars flare up and fade away. They see galaxies collide and merge. They are the silent, steadfast witnesses to the universe's grand, unfolding epic. Their peace is even deeper, their stability even more profound than that of their larger cousins. They hoard their energy, releasing it sparingly, a faint but constant warmth against the cold vacuum. Their internal fires burn with a slow, steady rhythm, a deep, almost meditative hum compared to the roaring furnaces of bigger stars. They are the universe settling in for the truly long haul, demonstrating patience on a scale that dwarfs even the mountains and oceans of the planets they might warm. Their eventual transition, when their hydrogen fuel finally begins to run low after aeons beyond counting, promises to be as gentle and unassuming as their long lives have been, a slow, quiet fading, a gradual sigh as their light dims over further immense stretches of time. Their sleepy time story is one of quiet endurance, a whisper rather than a shout. Now, turn your gaze towards the other path, the one taken by the big stars. These are the celestial titans, born with many times the mass of our Sun, sometimes 10, 20, 50, or even over 100 times more. From the moment they ignite, they are anything but quiet or unassuming. They are the brilliant beacons, the dazzling searchlights of the cosmos. Their immense mass creates an unbelievably powerful gravitational crush at their cores. This intense pressure drives their nuclear furnaces to unimaginable temperatures and ferocious rates of burning. They don't sip their fuel, they gulp it down with astonishing speed. They blaze across the interstellar darkness with a fierce, often bluish-white light, so bright they can outshine entire galaxies for a short while. Their main sequence, day, while still measured in millions of years, a vast span to us, is dramatically shorter than that of their smaller siblings. They live fast, burn bright, and leave a spectacular mark on their surroundings. Their surfaces churn with violent energy, and they blast powerful winds of particles out into space, sculpting the nebulae around them, seeding the void with heavier elements forged in their fiery hearts. They are the cosmic rock stars, brilliant, intense, and destined for a much shorter, more dramatic existence. Their peace, during their main sequence, is the peace of a coiled spring, a barely contained inferno. The balance between gravity and outward pressure is maintained, but it's a far more energetic, more precarious equilibrium. They pour out light and energy at rates thousands or even millions of times greater than our Sun. They illuminate vast clouds of gas, triggering the birth of new stars in their vicinity. They are cosmic engines of change, forging the heavier elements, the carbon, the oxygen, the iron that make up planets, and even ourselves, deep within their cores through the sheer force of their burning. But this spectacular brilliance comes at a cost. By consuming their hydrogen fuel so voraciously, they race through their reserves in what is, cosmically speaking, the blink of an eye. Their day is bright but brief. And just as their lives are lived on a grander, more intense scale, so too will be their departure. Their enormous mass means that when their fuel begins to falter, gravity's victory will be swift and dramatic. Their sleepy time story will not be a gentle fading like the little stars. It promises something far more spectacular, a final, transformative act that echoes across the cosmos, leaving behind remnants unlike anything the smaller stars could produce. So, you see, the path a star takes towards its eventual slumber is set from its very beginning. It all comes down to that initial gathering of cosmic material, the mass it accumulates in its stellar nursery. More mass means stronger gravity. Stronger gravity means a hotter, denser core. A hotter core means a much faster rate of nuclear burning. Faster burning means a shorter life, but often a more dramatic one, both during its shining phase and at its end. Less mass means a gentler gravitational squeeze, a cooler core, a much slower, more leisurely consumption of fuel, leading to an incredibly long, quiet life and a very different kind of fading away. Two paths, two distinct destinies, branching out from that long, peaceful day of the main sequence. One path is taken by the quiet, enduring little stars, destined for a slow, gentle transformation after an almost eternal glow. The other is walked by the brilliant, massive stars, living bright and fast, destined for a spectacular finale that seeds the universe anew. Both are natural, necessary parts of the great cosmic cycle of birth, life, and transformation. And understanding these two different sleepy time stories helps us appreciate the rich variety and intricate beauty woven into the fabric of the night sky. Each star, whether small and shy or large and brilliant, plays its part before eventually settling into its long rest. Let us follow, then, the path of one of those quiet, enduring little stars, one much like our own sun, perhaps, drifting through the velvet darkness. For billions upon billions of years, it has shone with a steady, gentle light, a reliable beacon in its corner of the cosmos. Inside its heart, deep within the core, the slow, patient alchemy of fusion has been turning hydrogen into helium, releasing the energy that pushes outwards, perfectly balancing the inward pull of its own gravity. It's been a long, peaceful existence, a seemingly endless summer afternoon of stellar life. The star has been content in its main sequence phase, diligently sipping its vast reserves of hydrogen fuel, never in a hurry, its light a constant, warm reassurance in the void. But even the longest afternoon must eventually yield to twilight. After eons of steady burning, the hydrogen fuel right in the very center of the star's core begins to run low. Imagine a hearth fire that has burned brightly all day, consuming the logs placed carefully in the middle. Now, only embers remain in that central spot. The main source of outward pressure, the fusion furnace that held gravity at bay, starts to sputter and fade in the core. The delicate balance that defined the star's long youth is beginning to waver, ever so slightly. Gravity, patient and persistent, senses this weakening. It never truly went away, always waiting, always pulling inwards. Now, with the outward push from core fusion diminishing, Gravity begins to gently, inexorably, squeeze the core inwards. The star's heart, now mostly helium ash from the long hydrogen burn, starts to contract under this renewed gravitational pressure. And just like squeezing a ball can make it warmer, this compression causes the core, even though it's no longer fusing hydrogen there, to heat up dramatically. It becomes denser and hotter than it ever was during its main sequence life. The embers glow fiercely as they are pressed together. This intense heat radiating from the contracting, non-fusing helium core has a remarkable effect. It warms the layers immediately surrounding the core, layers that still contain plenty of fresh hydrogen fuel, like untouched logs stacked around the central hearth. This surrounding shell of hydrogen reaches the critical temperature and pressure needed for fusion to begin. So, while the fire in the hearth has died down, a new, intense ring of fire ignites around it. Hydrogen fusion restarts, but not in the core anymore. It's now happening in a shell surrounding the incredibly hot, dense helium core. This shell burning is far more intense than the core burning ever was. It generates a tremendous amount of energy, pushing outwards with renewed vigor, far exceeding the gentle push of the star's youth. This powerful outward pressure begins to lift the star's outer layers, pushing them further and further away from the center. And this is where our little star begins its slow, magnificent transformation. It starts to swell, gently at first, then more profoundly. It's like the star is taking a deep, slow, cosmic breath, inhaling the surrounding space. Its outer layers, pushed by the fierce energy from the hydrogen-burning shell deep within, expand outwards, growing larger and larger over millions of years. This isn't a sudden explosion, not for these smaller stars. It's a gradual, majestic puffing up, a slow-motion expansion that will eventually make the star hundreds of times larger than it was during its long, stable life. Imagine our own sun undergoing this change. Billions of years from now, it too will follow this path. As it swells, it will grow so large that its outer edges might reach out and gently engulf the innermost planets, Mercury, Venus, perhaps even Earth. It's a quiet, almost inevitable consequence of this deep breath, this grand expansion. The star isn't being destructive, it's simply following the natural course set by the laws of physics, stretching out its arms as it enters a new phase of its existence. As these outer layers expand so dramatically, they spread the star's energy over a much, much larger surface area. Think of spreading a small amount of butter over a very large piece of toast. The layer becomes thinner and cooler. Similarly, the star's surface temperature drops, even though its core and the burning shell within are hotter than ever. This cooling surface changes the color of the light the star emits. Instead of the yellow-white light of its youth, it begins to glow with a cooler, softer, reddish-orange hue. And so, the star becomes what we call a red giant. Giant because it has swelled to an enormous size, puffing itself up like a grand celestial balloon. Red because its expanded surface is now cooler, emitting light towards the red end of the spectrum. It's a beautiful, serene phase, despite the dramatic changes happening deep inside. The star hangs in the darkness, a vast, luminous, softly glowing sphere, looking for all the world like it's taking a long, slow, peaceful sigh after its billions of years of steady shining. This red giant phase is not the end, but rather a profound transition. It's the star adjusting to its changing internal circumstances, finding a new, albeit temporary, equilibrium. The intense shell burning continues, creating more helium ash that falls onto the core, making the core even heavier and denser. The star remains in this puffed-up state for a considerable time, perhaps millions or even hundreds of millions of years, depending on its specific mass, a long time for us, but a relatively brief chapter in the star's multi-billion-year life story. It's a time of quiet grandeur. The star, now immense and glowing with a warm, rosy light, dominates its cosmic neighborhood in a new way. It's no longer the compact, intensely hot point of light it once was, but a vast, diffuse presence. Its outer layers are tenuous, almost ethereal, held loosely by the star's gravity, which struggles to keep hold of such a vastly expanded envelope. Little wisps of gas might even begin to drift away from the outermost edges, like gentle exhalations accompanying that deep, slow breath. This puffing up, this transformation into a red giant, is the destiny awaiting stars like our Sun, the smaller, more common stars scattered throughout the universe. It's their way of growing sleepy, not by simply fading out, but by taking this one last, grand, expansive gesture. They swell and cool on the outside, while deep inside, the preparations for the next stage of their slumber are slowly taking place within the contracting, superheated core. It is a testament to the slow, unhurried pace of cosmic evolution for these stellar elders, a gentle giant's breath before settling into an even deeper quietude. The universe watches, patiently, as the little star enjoys its majestic, red-glowing twilight years. And so, the gentle giant continues its slow exhale. The vast, rosy atmosphere, already tenuously held, begins to loosen its connection to the star within. It isn't a sudden break, not a violent expulsion, but more like letting go of a breath held for millennia. Imagine the finest, most delicate silk scarf, held loosely in an open hand. A soft breeze, almost imperceptible at first, begins to lift its edges, teasing the threads apart, encouraging them to drift. So too, the outermost layers of the red giant begin to lift away, responding not to a forceful push, but to a steady, rhythmic, nudging from deep within. Deep inside, where the core continues its dense, hot contraction, the surrounding shell where helium now burns is not perfectly stable. It flickers, sometimes pulsing with a little extra energy, like a slow, deep, internal heartbeat, sending gentle pressure waves rippling outwards. These pulses, arriving at the vastly expanded, loosely bound surface, are enough. They are the quiet encouragement the outer layers need to finally detach, to embark on their own journey into the surrounding space. It's a gradual release, layer by layer, like petals unfolding not from a bud, but from a fully bloomed flower finally letting go. Slowly, inexorably, a vast bubble of gas begins to swell outwards from the aging star. It moves with a dreamlike slowness, perhaps only 10 or 20 kilometers every second, which sounds fast to us, but on the cosmic scale, it is a leisurely drift. This expanding shell is carrying away the star's outer envelope. The hydrogen and helium that formed the bulk of its atmosphere, now enriched with traces of heavier elements forged during its long life and its time as a giant. It's like the star is unwrapping itself, shedding its old, familiar robes. As this cloud of stellar breath expands, moving further and further away, it thins and cools. For a time, it might be almost invisible, a ghostly sphere of neutral gas expanding into the darkness. But the star itself is undergoing a profound transformation at its heart. With the insulating outer layers drifting away, the incredibly hot, dense core is revealed. This tiny remnant, perhaps no larger than the Earth but containing nearly half the star's original mass, blazes with an intense, fierce light. It is incredibly hot, hundreds of times hotter than the surface of our own Sun, radiating fiercely in high-energy ultraviolet light. And this is where the magic happens. This is where the sigh becomes beautiful. The intense ultraviolet radiation pouring out from the exposed stellar core streams outwards, catching up with the slowly expanding shell of gas. When this harsh light strikes the atoms in the cloud, the hydrogen, the helium, the traces of oxygen, nitrogen, and carbon, it energizes them. It strips electrons away from the atoms, a process called ionization. But atoms prefer to be whole. Very quickly, the electrons recombine with their atoms, and as they do so, they release that captured energy, not as harsh ultraviolet light, but as visible light, soft and colorful. The invisible cloud begins to glow. It's as if the star's final breath is suddenly illuminated from within, transformed into a luminous masterpiece. The entire expanding shell lights up, becoming a celestial object of breathtaking beauty, a planetary nebula. The name is a little misleading, a historical accident from when early astronomers with small telescopes thought these fuzzy, glowing shapes resembled the faint disks of planets like Uranus or Neptune. But they are not planets, nor are they related to planet formation. They are the glorious, illuminated farewells of stars like our Sun. The colors are often spectacular, painting intricate patterns across the celestial canvas. The most abundant element, hydrogen, typically glows with a deep, warm red. Oxygen, energized in a particular way, shines with ethereal shades of green and sometimes blue, often concentrated in the hottest regions closest to the central star. Nitrogen might add its own reddish hues. These colors don't mix uniformly. They often appear in distinct shells or intricate structures, revealing details about the composition of the gas and the way it was shed by the star. Imagine looking at a vast, cosmic stained glass window, lit from behind by an intensely bright, tiny point of light. Filaments of emerald green might weave through clouds of ruby red, perhaps bordered by faint whispers of blue or violet. The light is soft, ethereal, not harsh or glaring. It has a delicate, almost fragile quality, a testament to the thinness of the glowing gas spread over enormous distances, often spanning a light year or more across. And the shapes. While some planetary nebulae appear as relatively simple spheres or rings, like the famous Ring Nebula, a perfect cosmic smoke ring puffed into space, many display far more complex and intriguing structures. Some are bipolar, resembling giant hourglasses or ethereal butterfly wings, suggesting the star shed its layers more vigorously from its poles than its equator, perhaps guided by the star's rotation or the presence of a strong magnetic field. Others show intricate knots, jets, and wispy filaments, hinting at complex interactions between the outflowing gas and the surrounding interstellar medium, or perhaps the gravitational influence of an unseen companion star orbiting the dying primary. We see bubbles within bubbles, sharp edges and soft, diffuse halos, symmetrical patterns and lopsided forms. Each planetary nebula is unique, a personal signature left by its parent star, sculpted by the details of its final, gentle expulsion and the environment into which it expands. They are like cosmic Rorschach tests, beautiful, ghostly shapes inviting wonder and contemplation. The Eskimo Nebula, with its fuzzy hood, the Cat's Eye Nebula, with its astonishingly complex, concentric shells, the Helix Nebula, resembling a vast eye staring across the cosmos, each tells a story of a star's quiet end. This spectacular display, however, is fleeting on cosmic timescales. The nebula continues to expand, relentlessly drifting outwards from its central star. As it expands, the gas becomes thinner and more diffuse. The central star, having exhausted its fuel for nuclear fusion, slowly begins to cool down, its intense ultraviolet radiation fading over tens of thousands of years. Gradually, the light that illuminates the nebula weakens. The beautiful colors soften, dim, and eventually fade away entirely. The expanding gas, now cool and dark once more, merges imperceptibly with the vast reservoir of gas and dust that fills the space between stars, the interstellar medium. The beautiful sigh fades into silence. The show is over, but it is not an ending without legacy. The elements forged inside the star and gently puffed away in the planetary nebula, the carbon, the nitrogen, the oxygen, enrich the surrounding space. This material mingles with primordial hydrogen and helium, becoming part of the raw ingredients from which new stars, new planets, and perhaps even new life will eventually form. Billions of years down the cosmic road, the star's final, beautiful breath is a gift back to the universe, a quiet contribution to the ongoing cycle of cosmic creation. And the tiny, hot core left behind at the center, it has played its final, illuminating role. It no longer produces energy through fusion. It is simply a cooling ember, destined to fade slowly over unimaginable eons. Its story continues, but the brief, radiant chapter of the planetary nebula, that moment of luminous artistry, has drawn to a close, leaving behind a memory of color and light in the quiet darkness. It was the star's gentle, beautiful letting go, a peaceful transition towards its final, quiet rest. Its story continues, not with the vibrant pulse of fusion, but with the quiet endurance of what remains. At the heart of the now dispersed ghostly nebula lies a tiny, intensely hot object, the core of the star laid bare. This is the final stage for stars like our Sun, a celestial ember known as a white dwarf. Imagine something incredibly small on a cosmic scale, perhaps only the size of the Earth, or even smaller. Yet, contained within this compact sphere is a staggering amount of material. often holding as much mass as our Sun originally did before it began shedding its outer layers. All that substance, squeezed into such a tiny volume, results in a density that defies everyday understanding. If you could somehow scoop up a teaspoonful of white dwarf matter, it would weigh several tons here on Earth, perhaps as much as a large truck. It's a state of matter unlike anything we experience directly, where atoms are crushed so close together that their fundamental structures begin to resist further compression. This resistance comes not from the familiar push and pull of heat and pressure that powered the star during its long life, but from the electrons themselves. Stripped from their atoms in the intense heat and pressure, these tiny particles are forced into incredibly close quarters. There's a fundamental rule in the quantum world, a deep unwillingness of these electrons to occupy the same state, the same tiny space. They push back, creating an outward pressure, a stubborn refusal to be squeezed any further. This quantum mechanical bulwark, this electron degeneracy pressure, is all that holds the white dwarf up against the relentless inward crush of its own gravity. Without the outward force of nuclear fusion, which ceased long ago, this electron resistance is the only thing preventing the star's core from collapsing entirely. So, the white dwarf sits there, incredibly dense, supported by the strange rules governing the very small. It is composed primarily of the ashes of the star's long life of fusion, mostly carbon and oxygen, the products of helium burning deep within the core during its red giant phase. These elements are locked together in a crystalline lattice structure as the core cools, though initially it is an incredibly hot fluid of atomic nuclei swimming in a sea of degenerate electrons. There are no new elements being forged here. The fires have gone out. The star, as a living, breathing engine of creation, is no more. What remains is its legacy, compressed into a tiny, enduring jewel. But though the furnace is extinguished, the white dwarf still shines. It glows with a fierce, brilliant light, initially white-hot, hence its name. This light isn't generated by ongoing reactions. It's simply the leftover heat, the residual thermal energy from billions of years of nuclear burning and the gravitational collapse that formed it. Imagine pulling a glowing poker from a blacksmith's forge. It continues to radiate heat and light long after it's removed from the fire. The white dwarf is like that, but on an astronomical scale, possessing an immense reservoir of stored heat. Its surface temperature can initially be incredibly high, perhaps soaring to over 100,000 degrees Celsius, far hotter than the surface of our own Sun. This intense heat, radiating from such a small surface area, makes the newly formed white dwarf blaze fiercely in the ultraviolet and visible spectrum, a tiny beacon against the dark. Yet, this brilliance is finite. Without any internal energy source to replenish the lost heat, the white dwarf embarks on the slowest, most gradual cooling process imaginable. It radiates its energy away into the vast emptiness of space, photon by photon, whisper by whisper. This is not a rapid dimming, but a cooling that unfolds over timescales that dwarf the current age of the universe. Billions upon billions, even trillions of years, will pass as the white dwarf slowly relinquishes its stored thermal energy. It is like the universe's most patient ember, glowing softly in the cosmic hearth. As it cools, its color will slowly change. The initial, intense, white-hot glow will gradually soften, shifting towards yellow, like our Sun. Over further vast stretches of time, as more heat escapes, it will cool further, its light becoming tinged with orange, then deepening into a dull, ruddy red. Its luminosity, its intrinsic brightness, will diminish steadily with its temperature. It becomes fainter and fainter, harder and harder to detect, retreating slowly into the background darkness. This process is incredibly slow, so slow that the universe itself is not yet old enough for any white dwarf to have completed its cooling journey. Eventually, after aeons have passed, a duration perhaps 1,000 times longer than the universe has currently existed, the white dwarf will have radiated away almost all its heat. Its temperature will drop so low that it no longer emits significant visible light, or indeed much radiation at all. It will become a cold, dark sphere of degenerate matter, drifting silently through space. Astronomers call this hypothetical final state a black dwarf. It's important to remember that these are theoretical objects. The timescale for a white dwarf to cool to this point is so staggeringly long that none are expected to exist yet. The universe is simply too young. So, the white dwarf represents a kind of peaceful, stable retirement for a star like our Sun. It is the endpoint of its energetic life, a compact monument to the nuclear reactions that once blazed within. It no longer shapes its surroundings with powerful winds or brilliant radiation as it did in its youth or even during the planetary nebula phase. Instead, it simply exists, a dense, quiet sphere, slowly releasing its ancient warmth into the void. Its presence is a testament to the cycles of stellar life and death, a reminder that even after the grand spectacle fades, something enduring often remains. Studying these faint embers provides astronomers with invaluable clues. By finding white dwarfs in star clusters, scientists can estimate the age of the cluster itself, as the coolest, faintest white dwarfs must be the oldest, having had the longest time to radiate their heat away. They are cosmic clocks, ticking down with unimaginable slowness. They also confirm our understanding of stellar evolution, showing us the fate that awaits the vast majority of stars in the universe, including our own Sun, billions of years from now. The white dwarf's existence is serene. It faces no further dramatic transformations, barring rare interactions with a companion star, which can lead to other phenomena like novae or certain types of supernovae. But for an isolated white dwarf, the path is one of quiet fading. It floats through the interstellar medium, a tiny, dense ghost, holding the memory of the star it once was. Its faint sparkle is a whisper from the past, a story of fusion and light now concluded, leaving behind only this incredibly dense, slowly cooling relic. It is the star's final, quiet form, destined to drift through the cosmos for eternity, eventually becoming invisible, a cold, dark cinder returning peacefully to the background temperature of the universe. A faint sparkle, slowly, patiently, fading into the long night. But not all stars fade so quietly into the long night. For those celestial bodies born with truly prodigious mass, many times greater than our own Sun, the final chapters of their existence are written not in gentle whispers, but in declarations of astonishing scale. Their lives are lived in the fast lane of the cosmos, burning through their fuel reserves with breathtaking speed, and their end stages are correspondingly grand, marked not by shrinking and cooling, but by a period of staggering expansion. This is the story of how the universe's biggest stars prepare for their truly grand finale, by first getting even bigger. Imagine a star born perhaps 10, 20, or even 50 times the mass of our Sun. From its very beginning, it is a different creature altogether. Its immense gravity crushes its core with unimaginable force, creating temperatures and pressures far exceeding those in smaller stars. This inferno drives nuclear fusion at a furious rate. While our Sun leisurely fuses hydrogen into helium over billions of years, these giants blaze through their core hydrogen in a cosmic blink, perhaps only a few million years. They shine with an intense blue-white light, thousands or even millions of times more luminous than the Sun, dominating their stellar neighborhoods. But this brilliance comes at a cost, a short and dramatic life. When the hydrogen fuel in the core is finally exhausted, the outward radiation pressure from fusion ceases. Gravity, ever present and relentless, immediately begins to win. The core, now composed primarily of helium ash, starts to contract under its own immense weight. Just as squeezing a gas makes it hotter, this gravitational collapse heats the core to ever more extreme temperatures, reaching perhaps 100 million degrees Celsius, or even more. While this core collapse is happening, something crucial occurs in the layers immediately surrounding it. Here, hydrogen is still abundant, and the rising temperatures from the collapsing core ignite a shell of hydrogen fusion. This shell burning adds yet more energy, pouring heat outwards. Deep within the contracting core, the temperature eventually becomes so high that a new fusion process can begin. Helium nuclei, the leftovers from the first stage of fusion, are forced together. 3 helium nuclei combine to form a carbon nucleus, releasing another burst of energy. Sometimes, a further helium nucleus can fuse with a carbon nucleus to create oxygen. The star has found a new lease on life, tapping into a new fuel source at its heart. Now, the star has 2 powerful energy sources, helium fusion blazing away in the core, and hydrogen fusion continuing furiously in a shell wrapped around that core. The sheer amount of energy being generated deep within the star becomes overwhelming. This outward flood of energy exerts a tremendous pressure, pushing against the star's outer layers. Gravity, which holds the star together, is still powerful, but the outward radiation pressure from these nested fusion zones begins to dominate, especially in the vast, overlying envelope of gas that makes up the bulk of the star's volume. And so, the star begins to swell. Slowly, inexorably, its outer layers lift away from the intensely hot core, expanding outwards like an unimaginably vast balloon being steadily inflated. This expansion is colossal. The star, already a giant, begins to grow to truly monstrous proportions. It balloons outwards, reaching sizes hundreds or even 1,000 times the diameter of our Sun. If such a star were placed where our Sun is, its outer edges would engulf the orbits of Mercury, Venus, Earth, and Mars, perhaps even stretching out towards Jupiter. It becomes a red supergiant. Why red? As the star's outer layers expand, the energy generated deep within is spread over an immensely larger surface area. Imagine stretching a small hot piece of glowing metal into a vast thin sheet. The sheet will be much cooler overall. Similarly, the star's surface cools significantly, dropping from tens of thousands of degrees Celsius in its youth down to perhaps only 3, 0 or 4, 0 degrees. This cooler temperature causes its light to shift towards the red end of the spectrum, giving it a characteristic deep orange or ruby glow. It's a slightly deceptive name, however. While its surface is cooler, the total amount of energy it radiates is still immense due to its sheer size, making it one of the most luminous types of stars in the universe, pouring out light, much of it in the infrared spectrum. The star is now a paradox, incredibly massive, yet extraordinarily diffuse in its outer regions. Its core remains unimaginably dense and hot, but its vast, bloated envelope is thinner than the best vacuum we can create on Earth. It's like a colossal, glowing fog bank, stretching across billions of kilometers. Its surface is not sharp and defined like the Sun's, but hazy and indistinct. Huge convection currents, like continent-sized bubbles in a cosmic cauldron, rise and fall within its outer layers, causing the star's brightness to vary, sometimes dramatically, over weeks or months. These giants often pulsate, rhythmically swelling and shrinking slightly, breathing like vast cosmic beings. Deep inside, the processes become even more complex. As the helium in the core runs out, gravity once again takes hold, compressing the carbon-oxygen core further. If the star is massive enough, the core temperature will rise yet again, high enough to ignite carbon fusion, creating heavier elements like neon, sodium, and magnesium. This pattern repeats: core fuel exhaustion, gravitational contraction, rising temperatures, ignition of new fusion processes, while the previous stage of fusion continues in a shell around the new core. Like a cosmic onion, the star develops nested shells, each fusing different elements: helium around the carbon-oxygen core, hydrogen around the helium shell. In the most massive stars, this process continues, building up shells of neon, oxygen, and eventually silicon fusion, all surrounding a final core of iron. Each stage burns faster than the last, the silicon to iron fusion perhaps lasting only a single day. During this red supergiant phase, the star's grip on its outer layers is tenuous. The immense radiation pressure pushing outwards, combined with the relatively weak surface gravity due to the star's enormous size, makes it easy for material to escape. Powerful stellar winds, far stronger than our Sun's solar wind, blow vast quantities of gas and dust off the star's surface and out into interstellar space. Over its time as a supergiant, the star can lose a significant fraction of its initial mass this way, seeding the surrounding cosmos with the heavier elements forged deep within its core, the carbon, oxygen, and other elements essential for building planets and, eventually, life. We see this shed material as beautiful nebulae surrounding some supergiants, ghostly shrouds hinting at the star's ongoing transformation. This swollen, luminous, yet unstable state is the star's penultimate form. It is a magnificent, imposing presence in the galaxy, a beacon visible across vast cosmic distances. But it is a temporary phase, a prelude. The intricate dance of fusion and gravity deep within its core is building towards a final, inevitable crisis. The creation of an iron core signals the end, as iron fusion consumes energy rather than releasing it. Gravity is poised for its ultimate victory. The star has become immense, a red supergiant, fulfilling the getting bigger part of its grand finale. But this very enormity sets the stage for an end far more spectacular, far more energetic than the quiet fading of its smaller cousins. The giant holds its breath, vast and glowing, balanced precariously on the edge of its final, dramatic act. The quiet drift of the white dwarf is one path. This immense, radiant swelling is another, leading towards a very different kind of night. And so, the giant star waits, suspended in the velvet dark. Deep within its heart, the silence is profound, yet heavy with anticipation. The core, now a dense sphere of iron ash, offers no more warmth, no more outward push from fusion's fire. It simply sits, gathering mass, growing heavier with each passing second as silicon fuses in a shell around it, raining down yet more iron. Gravity, patient for so long, begins to sense its moment. The delicate balance that held the star aloft for millions of years, the equilibrium between the outward press of light and heat and the inward pull of its own immense mass, is finally, irrevocably broken. The iron core has become too heavy, too dense, for even the incredible pressure of degenerate electrons. A quantum mechanical resistance that had been holding firm to support. It has reached a critical threshold, a point of no return, like a keystone gently removed from an immense arch. Imagine holding a perfect heavy sphere in your hands, feeling its weight settle, its solidity. Now imagine that sphere suddenly, impossibly, deciding to become smaller, denser, pulling itself inwards with unstoppable force, collapsing under its own tremendous presence. This is what happens in the heart of the star, in the quiet center of the vast, glowing supergiant. In less time than it takes for you to blink, the core gives way. Gravity wins its long-contested battle, its victory swift and absolute. The iron heart, perhaps the size of our own Earth, but containing the mass of nearly 1.5 suns, collapses catastrophically inward. It falls in upon itself at incredible speeds, a significant fraction of the speed of light. The star doesn't just shrink, it implodes with breathtaking violence. A volume the size of a planet crushes down, 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 in a fraction of a second, into a space no larger than a city nestled on Earth's surface. The density becomes almost beyond comprehension. Atomic nuclei squeeze together so tightly they begin to merge, losing their individual identities in the crush. This inward rush, this furious compression, cannot continue forever. There is a limit to how tightly matter can be packed. As the core collapses, the immense pressure forces protons and electrons to combine, creating neutrons, and releasing a ghostly flood of particles called neutrinos. These neutrinos carry away vast amounts of energy, streaming out from the core almost unimpeded. What remains of the core becomes something new, something extraordinarily dense, a proto-neutron star. It is an object composed almost entirely of neutrons, packed together as tightly as the fundamental forces of nature allow. It is now incredibly stiff, incompressible, like hitting solid diamond after falling through miles of empty air. The infalling material from the star's outer layers, still plummeting inwards from the regions above, unaware the floor has vanished and then reappeared as an impenetrable wall, slams into this newly formed, rigid surface. And it bounces. It's not a gentle bounce, like a child's ball hitting the pavement. It is perhaps the universe's most powerful recoil. An unimaginably energetic rebound wave, a shock wave of monumental proportions, is born from this abrupt halt and reversal deep within the star's center. This shock wave begins to surge outwards, carrying with it a tremendous amount of energy unleashed by the gravitational collapse. It plows back through the material that is still raining down onto the core, a tsunami of pure force fighting its way upstream against the relentless current of infalling stellar matter. For a critical moment, it seems the shock wave might stall, its outward push smothered by the sheer weight of the star collapsing upon it, like a swimmer caught in a powerful undertow. But here, the ghostly neutrinos play a crucial role. As they stream out from the newly formed neutron core, though they interact very weakly with matter, their sheer numbers are overwhelming. Passing through the dense, stalled material just behind the shockwave, they deposit a tiny fraction of their immense energy, but it's enough. It's like a sudden, collective push from behind, re-energizing the faltering shockwave, giving it the final, decisive impetus it needs to overcome the infalling tide and continue its journey outwards. The revitalized shockwave now blasts outwards with renewed ferocity, tearing through the overlying layers of the star, the shells where silicon, oxygen, carbon, helium, and hydrogen had been fusing or resting for millennia. It surges through them like an irresistible force moving through calm water, but this water is stellar plasma heated to millions of degrees. These layers have existed in a relatively peaceful state for the star's long life. Now, in mere hours, they are met with a wave of unimaginable violence and transformation, traveling at thousands, even tens of thousands, of kilometers per second. The shockwave heats the material it passes through to billions of degrees, triggering a final, frantic burst of nuclear fusion. But this is not the gentle, life-sustaining fusion that powered the star for aeons. This is explosive nucleosynthesis, a fleeting, violent forging process occurring in the wake of the shockwave. In the unimaginable heat and pressure, conditions are met that allow for the creation of elements heavier than iron, silver, gold, tin, lead, platinum, uranium, elements that could never be formed during the star's normal, stable lifetime. All the precious metals, the rare earths, the elements beyond iron in the periodic table that make up our complex world, are synthesized in these fleeting, fiery moments of the star's death throes. As the shockwave races towards the star's surface, the star itself remains, for a few precious hours, outwardly unchanged to a distant eye. An astronomer watching from a far-off world would see the familiar, bloated red supergiant, perhaps dimming just slightly as its core collapses, utterly unaware of the titanic struggle and incredible alchemy unfolding deep within its hidden heart. Then, without further warning, the shockwave breaks through the star's visible surface, the photosphere. It erupts from the star like the universe's most spectacular firework display, a dazzling flash of light that momentarily illuminates the cosmic neighborhood. This is the supernova. In an instant, the dying star becomes brighter than billions of ordinary stars combined, briefly capable of outshining its entire host galaxy. The light is almost blindingly intense, a torrent of photons unleashed across the entire electromagnetic spectrum, from the highest energy gamma rays and X-rays, through visible light, down to infrared and radio waves. It's a brilliant beacon announcing the star's dramatic demise, a signal visible across millions, even billions, of light-years of intervening space. This incredible burst of light, carrying an amount of energy equivalent to what our own sun will radiate over its entire 10 billion-year lifetime, travels outwards into the void, a spherical shell of pure brilliance expanding at the speed of light, carrying the news of the star's end. Following closely behind the initial flash of light comes the matter itself. The star's outer layers, now enriched with the full spectrum of newly synthesized heavy elements and accelerated to incredible speeds by the passage of the shockwave, are flung outwards into interstellar space. This expanding cloud of stellar debris travels at tremendous velocities, perhaps up to 10% of the speed of light initially. It forms a beautiful and intricate structure known as a supernova remnant. We see these remnants scattered across our galaxy, and in others, stunning, glowing tapestries of gas and dust, often appearing as delicate, interwoven filaments and colorful, wispy clouds, like the famous Crab Nebula, the remnant of a supernova seen on Earth nearly 1,000 years ago, or the delicate lacework of the Veil Nebula. They are beautiful memorials to the star that once shone so brightly, ghostly shells still expanding outwards into space thousands of years after the initial, cataclysmic explosion. Within these colorful clouds drift the elements forged deep within the star's core during its long life, and all the heavier elements created in its final, explosive moments. Carbon, nitrogen, oxygen, silicon, sulfur, iron, and onwards to gold, silver, lead, and uranium, the very building blocks of future stars, planets, asteroids, and indeed, The atoms within our own bodies are scattered far and wide through the galaxy. The supernova, therefore, is not merely an ending, a final destructive act. It is also a profound act of cosmic recycling and powerful creation. The star, in its spectacular death throes, seeds the surrounding interstellar medium with the heavy elements necessary for future generations of stars and planets to form, enriching the raw material of the galaxy. The powerful shockwave itself, as it expands outwards, can compress nearby clouds of cold gas and dust, pushing them over the edge to collapse under their own gravity and trigger the formation of entirely new stars and planetary systems. The death of one massive star can thus become the catalyst for the birth of countless others, perhaps even seeding those new systems with the ingredients for life. It is a magnificent cycle of destruction and renewal played out on the grandest possible scale. The dazzling flash of the supernova fades over weeks and months, but the expanding remnant continues its slow, majestic journey outwards, carrying the echoes of that final, fiery breath. But while the star's outer garments drift away like luminous smoke rings across the cosmic ocean, something profound may have occurred back at the very center, at the heart of the cataclysm. Not all of the star's substance is always flung outwards. Sometimes, amidst the unimaginable violence of the supernova, the core itself survives, transformed into one of the most extraordinary objects in the entire universe. Imagine, if you will, the immense star that once was, a vast, burning sphere, perhaps millions of miles across, dwarfing our own sun. Now, picture the very heart of that star, the engine room where fusion once blazed. During the supernova, as the outward pressures failed, gravity, that relentless, patient force, seized its ultimate victory over the core. In a fraction of a second, this core, already incredibly dense, collapsed inwards upon itself with unimaginable force. It didn't just shrink, it imploded, crushed down beyond all familiar comprehension. What can remain after such an event is something utterly astonishing, a neutron star. The name itself offers a clue, a whisper of the extreme transformation that has taken place, but the reality is difficult to truly grasp. Think of the size first. A neutron star is tiny, almost comically small when compared to the star it once belonged to, or even to planets like our Earth. It might measure only 10 or 20 miles across. Imagine a sphere roughly the size of a large city, perhaps like London or Manhattan, floating silently in the vast emptiness of space. That is the scale we are talking about, a stellar core compressed into the dimensions of a bustling metropolis. It seems impossibly small, a mere speck against the backdrop of the cosmos, easily lost in the immensity. You could, in theory, fly around it in a spaceship in just a few minutes. Compared to the star that birthed it, it is like comparing a single grain of sand to a towering mountain. Yet, contained within that tiny volume is an astonishing amount of matter. Typically, a neutron star packs more mass than our entire sun into that city-sized ball. Our sun, remember, contains over 99% of all the mass in our solar system. The planets, moons, asteroids, all mere crumbs by comparison. Now, take all of that, perhaps even 1.5 times that, or even twice the sun's mass, and squeeze it relentlessly, forcing it down, down, down until it fits within the confines of that small sphere, just a few miles wide. The result is a density that defies our everyday experience, a density so extreme that the familiar rules of matter begin to break down. Imagine trying to lift just a tiny piece of this neutron star material, perhaps a piece no bigger than a sugar cube or a child's playing die. If you could somehow bring such a fragment to Earth, it would weigh billions of tons. It would weigh more than entire mountains, more than vast fleets of ocean liners all piled together. A single teaspoonful of neutron star matter would outweigh Mount Everest. It would plummet through the Earth's crust as if it were mere mist, drawn down towards the planet's core by its own unbelievable weight. How can anything become so dense? It happens because, during that final, catastrophic collapse of the star's core, the pressure becomes overwhelming, truly astronomical. It overcomes the forces that normally keep atoms separate, the forces that define the shape and structure of matter as we know it. Atoms themselves are mostly empty space, a tiny nucleus surrounded by electrons orbiting at relatively vast distances. But in the forming neutron star, This empty space is violently eliminated. The immense gravitational pressure crushes the atoms completely. Electrons are forced, quite literally, into the protons within the atomic nuclei. Normally, these particles, the negatively charged electrons and the positively charged protons, repel each other or exist in distinct states. But here, gravity's grip is too strong. An electron and a proton merge together to become a neutron, a particle with no electrical charge. This process happens over and over again throughout the collapsing core. What's left is a sphere composed almost entirely of neutrons, packed cheek by jowl, touching each other, with virtually no space left between them. It's like taking all the empty space out of matter and leaving only the solid bits, squeezed together as tightly as the laws of physics will allow. This state of matter, this ultra-dense sea of neutrons, is called neutronium, a substance unlike anything found naturally on Earth. The star has become, in essence, a single, gigantic atomic nucleus, bound together not by the nuclear forces within an atom, but by its own stupendous gravity. And the gravity of such an object is just as mind-bending as its density. Because so much mass is packed into such a tiny volume, the gravitational pull at the surface of a neutron star is immense, hundreds of billions of times stronger than the gravity we feel here on Earth. If you could somehow stand on the surface of a neutron star, which you absolutely couldn't, as you'd be instantly flattened into a microscopic smear, you would weigh billions of times more than you do now. Escape from such a gravitational field requires incredible speed, a significant fraction of the speed of light itself. Light passing nearby is noticeably bent by the neutron star's gravity, its path warped by the extreme curvature of spacetime around this compact object. It acts like a powerful gravitational lens, distorting the view of stars and galaxies behind it. Even light emitted from the neutron star's own surface has to struggle mightily to escape, losing energy in the process, a phenomenon called gravitational redshift. The very fabric of space and time is profoundly warped in the vicinity of this tiny, super-strong stellar remnant. So, while the beautiful supernova remnant expands outwards, seeding the galaxy with new elements and triggering new star birth, at the site of the explosion, this tiny, dark, incredibly massive object might remain. It is a quiet testament to the overwhelming power of gravity, a silent monument forged in the heart of a stellar catastrophe. It is not empty space left behind, but rather matter compressed to its absolute limit, a city-sized sphere holding the mass of suns, composed of neutrons packed edge to edge. It sits there, a tiny point of unimaginable density and strength, a truly super tiny, super strong leftover from the life and death of a massive star. It represents one possible final chapter, one extraordinary transformation in the grand, cosmic story of stellar evolution. It is a whisper of the extremes the universe can reach, a quiet, dense point of wonder in the darkness. But the neutron star, this incredibly dense sphere of tightly packed neutrons, is only one possible ending to the story of a truly massive star. Sometimes, when the star that collapses is exceptionally large, perhaps many tens of times more massive than our own sun, even the extraordinary pressure of neutrons crammed shoulder to shoulder is not enough. Sometimes, gravity's victory is absolute. Imagine, if you will, the core of such a colossal star, after the supernova blast has ripped the outer layers away. The core itself is still immensely heavy, far heavier than the cores that form neutron stars. The inward crush of gravity continues, relentlessly. The neutrons, already touching, are squeezed further still. There is simply no known force in the universe that can withstand this final, ultimate compression. The collapse doesn't stop. It continues, faster and faster, pulling everything inward with an intensity that beggars belief. The material crushes down, smaller than a city, smaller than a mountain, smaller perhaps than a grain of sand, yet still containing the immense mass of several suns. It collapses seemingly towards a single point, a concentration of mass and gravity so profound that it fundamentally changes the nature of space and time around it. What happens at that central point is a deep mystery, a place where our understanding of physics falters. But what we can understand is the effect this collapsed object has on its surroundings. As the core shrinks, the gravitational pull at its surface becomes unimaginably strong. Think of gravity like a slope you have to climb to get away. For Earth, It's a gentle slope. A rocket needs speed, but it can escape. For a neutron star, the slope is tremendously steep, requiring immense energy to leave. But for this object, born from the ultimate collapse, the slope becomes effectively infinite. There comes a point, a boundary in space surrounding this collapsed core, where the required escape velocity, the speed needed to climb out of that gravitational slope, becomes greater than the speed of light itself. And since nothing in the universe can travel faster than light, this boundary marks a point of no return. Anything that crosses this threshold, matter, light, information, can never, ever get back out. It is trapped forever by the overwhelming gravity. This boundary isn't a physical surface you could touch. It's an invisible demarcation line, a one-way membrane woven into the fabric of space-time itself. It is called the event horizon. And the region within this boundary, this place defined by gravity so strong that even light is imprisoned, is what we call a black hole. It is not a hole in the sense of being empty. It contains all the crushed mass of the original stellar core, but it is black, because no light can escape from within its event horizon to reach our eyes or telescopes. It emits no light of its own, nor can it reflect any. It is fundamentally invisible, a patch of perfect blackness against the backdrop of space. It is less a thing, and more a place, a region where gravity reigns supreme and dictates the ultimate fate of anything that ventures too close. So how can we possibly know these invisible wonders exist if they cannot be seen directly? We look for their influence, the way their immense gravity subtly, or sometimes dramatically, affects the things around them. Imagine watching a star through a powerful telescope, night after night. You see it moving, tracing an orbit through space, but it seems to be orbiting nothing. There's no visible companion star pulling it along in this cosmic dance. Yet, its precise path tells astronomers there must be something massive there, something unseen, pulling it with an invisible gravitational tether. By carefully measuring the star's orbit, its speed, its shape, the time it takes to go around, scientists can calculate the mass of the invisible partner. If that mass is very large, several times the mass of our Sun, yet crammed into a space so small it emits no light, the inescapable conclusion is that the unseen partner must be a black hole. The star becomes a lonely dancer, waltzing with an invisible presence. Sometimes the evidence is more dramatic. If a black hole happens to have a nearby companion star, its powerful gravity can siphon material away from that star. Gas, mostly hydrogen and helium, gets pulled off the companion in a long stream, like water spiraling down a drain. But this isn't a gentle trickle. As the gas falls towards the black hole, it doesn't go straight in. Instead, it swirls around it, faster and faster, forming a flattened, spinning structure called an accretion disk. The gas molecules rub against each other with incredible friction in this high-speed cosmic whirlpool. This friction heats the gas to millions, even billions of degrees, far hotter than the surface of any star. At these extreme temperatures, the gas glows fiercely, not necessarily in visible light, but in high-energy forms like X-rays. Astronomers can detect these intense X-ray emissions using special space telescopes. They see a bright source of X-rays flickering in the sky, often associated with a normal star that seems to be losing mass. This glowing, superheated disk acts like a beacon, signaling the presence of the invisible black hole at its center. The light doesn't come from the black hole itself, but from the matter caught in its gravitational embrace, a final, brilliant cry before it crosses the event horizon and disappears from view forever. It's like seeing the swirling water at the top of a waterfall, brightly lit, even though the depths below are hidden. And just like their less extreme cousins, the neutron stars, black holes also warp spacetime around them profoundly. Light passing near a black hole, but not close enough to fall in, has its path bent significantly. This effect, gravitational lensing, can distort the images of stars and galaxies lying behind the black hole from our point of view. We might see multiple images of a distant galaxy, or its shape might be stretched and warped into strange arcs, like looking through the curved base of a wine glass. Observing these distortions can be another clue, another way to infer the presence of a massive, invisible object bending light with its extraordinary gravity. So, While we cannot see the black hole itself, we can see its gravitational shadow play, the lonely dance of an orbiting star, the incandescent swirl of an accretion disk shouting in X-rays, the warped light from distant galaxies passing by. These are the whispers and echoes that betray the existence of these invisible giants. What lies deep inside, beyond the event horizon? What happens to matter when it collapses towards that central point, the singularity, where density and gravity theoretically become infinite? Here, our current laws of physics break down. We simply don't know. It is a frontier of human knowledge, a place where gravity and quantum mechanics must somehow reconcile, hinting at new physics yet to be discovered. Perhaps it is a gateway to somewhere else. Perhaps it is the ultimate endpoint of matter. Or perhaps it is something stranger still. For now, it remains shrouded in mystery, a silent question mark hanging in the cosmos. These stellar black holes, born from the collapse of individual massive stars, typically have masses a few times to perhaps a few tens of times that of our Sun, all contained within an event horizon perhaps only tens of kilometers across. They are the quiet, dark siblings to the neutron stars, another possible final resting place for stars that lived fast and died young. But the universe, in its grandeur, also creates black holes on vastly larger scales. At the heart of almost every large galaxy, including our own Milky Way, lurks a supermassive black hole, weighing millions or even billions of times the mass of our Sun. These giants likely form differently, growing over cosmic time by merging with other black holes and consuming vast amounts of gas and stars. They are the gravitational anchors around which entire galaxies revolve, cosmic behemoths whose origins and influence shape the evolution of the universe on the grandest scale. Yet, whether stellar mass or supermassive, the essence remains the same, a region defined by gravity's ultimate triumph. The black hole represents an end state, a place of profound silence and darkness, yet also a place of incredible power and deep mystery. It is the universe demonstrating the sheer, overwhelming force of gravity, capable of crushing matter beyond recognition and warping the very fabric of reality. It is another extraordinary possibility woven into the life cycle of stars, a silent, invisible wonder inviting us to contemplate the deepest secrets of space, time, and existence itself. It sits there, not as empty space, but as a concentration of potential and mystery, a quiet testament to the universe's ability to create phenomena far stranger and more wonderful than we might ever have imagined. It is a final, deep breath held in the darkness, waiting. While gravity holds its profound, silent court in those deep, unseen places, the vast ocean of space around them continues its own gentle, unhurried rhythm. The universe does not only end things, it is perpetually beginning. That final, deep breath, held in the darkness of a black hole, is but one possibility, one quiet pause in the cosmic symphony. Elsewhere, the echoes of other stellar lives are already beginning to stir, carrying the seeds of rebirth across the interstellar void. Imagine, if you will, a star much like our Sun, but nearing the end of its long life. Not massive enough to collapse into utter darkness, it instead performs a final, graceful act of letting go. Over thousands of years, it gently puffs its outer layers away, shedding them like softly colored veils into the surrounding space. These expanding shells of gas, illuminated by the fading hot core of the star left behind, a white dwarf, create some of the most beautiful sights in the cosmos, planetary nebulae. They look like celestial smoke rings, or ghostly butterflies, or perhaps a single, luminous eye gazing out into the darkness. They are ethereal, fleeting structures, lasting only a few tens of thousands of years, a mere blink in cosmic time, but within their delicate beauty lies a precious gift. These expanding clouds are rich with elements like carbon, nitrogen, and oxygen, elements forged over billions of years in the star's core, and now gently return to the interstellar medium like a quiet sigh releasing held breath. For stars much more massive, the end is far more dramatic. A supernova explosion, a brilliant, catastrophic announcement of its demise. We often think of the violence, the incredible energy unleashed. But even in this spectacular end, there is the beginning of something new. The explosion rips the star apart, blasting its contents far and wide at tremendous speeds. This expanding debris field, known as a supernova remnant, is a turbulent, chaotic place initially, a shockwave plowing through the surrounding space, heating gas and dust to millions of degrees. Yet, within this maelstrom are scattered not just the lighter elements, but the heavier treasures forged only in the unimaginable heat and pressure of the star's final moments and the explosion itself. Elements like silicon, sulfur, iron, nickel, and even rarer, heavier atoms like gold and uranium. Everything heavier than iron owes its existence to these explosive cosmic endings. These remnants, like the famous Crab Nebula, are glowing tapestries woven from the very substance of the dead star, intricate clouds of enriched material flung outwards, destined to mix with the wider cosmos. Whether released in the gentle sigh of a planetary nebula or the explosive shout of a supernova, this stellar material, this stardust, begins a long, slow journey. It drifts through the immense emptiness between the stars, joining the vast, diffuse clouds of gas and dust that already linger there, remnants of previous generations of stars, and the primordial hydrogen and helium left over from the Big Bang itself. These interstellar clouds are incredibly tenuous, far more rarefied than the best vacuum we can create on Earth. Yet, they stretch for light years, vast reservoirs of potential. Picture these clouds, perhaps illuminated by the light of distant, unrelated stars, glowing faintly in hues of pink and blue, or sometimes appearing as dark silhouettes against a brighter background. They are not static. They drift and swirl in slow, majestic currents, influenced by the gravity of the galaxy, the shock waves from other supernovae, and the radiation pressure from bright, young stars. Within these clouds, the newly dispersed elements, the carbon, the oxygen, the iron, mingle with the ancient hydrogen and helium. They cool down over millions, even billions of years. Atoms find each other, bonding to form simple molecules, then more complex ones. Tiny grains of dust, perhaps coated with water, ice, or frozen methane, begin to form microscopic specks of solid matter built from the ashes of dead stars. This vast, enriched expanse is the inheritance of the cosmos, a celestial fallow field waiting for new seeds to sprout. And a force that will eventually gather this diffuse material is the same one that governs the fates of the most massive stars and holds galaxies together: gravity. Though its pull is incredibly weak across these vast distances and amongst such sparse material, gravity is patient. It is relentless. Over immense timescales, subtle variations in density within the clouds become amplified. Regions that are just slightly denser than their surroundings begin to attract more material. Slowly, almost imperceptibly, wisps of gas and dust begin to draw together. Imagine a slow inward drift, a convergence happening on a scale almost too vast to comprehend. What was once a diffuse, formless cloud begins to fragment into smaller, denser clumps. These clumps continue to contract under their own gravity, pulling in more and more material from their surroundings. They become colder, denser, darker, vast molecular clouds, the true nurseries of stars. Inside these dark cocoons, shielded from the harsh radiation of existing stars, the conditions become right for the next stage of creation. The temperature drops low enough for molecules, especially hydrogen molecules, to thrive. The density increases. Within the heart of these collapsing clumps, gravity's pull becomes ever stronger. The material falls inwards faster and faster, piling up at the center. The core of the clump begins to heat up due to the compression, like air warming in a bicycle pump. It starts to glow dimly, first in infrared light, invisible to our eyes but detectable by specialized telescopes. This glowing core is a protostar, a star in the making, still shrouded in the dusty cocoon of its birth cloud. Around it, the remaining gas and dust often flatten into a spinning disk, a protoplanetary disk, where planets might eventually form. The protostar continues to gather mass, its core growing hotter and denser. Eventually, the pressure and temperature at its very center reach a critical point, millions of degrees. At this threshold, a new miracle occurs. Nuclear fusion ignites. Hydrogen atoms begin to fuse together to form helium, releasing a tremendous amount of energy in the process. This outward rush of energy pushes against the inward pull of gravity, establishing a delicate balance, a star is born. Its light shines out, clearing away the remnants of its birth cocoon, illuminating the surrounding space. And what is this new star made of? Primarily hydrogen and helium, yes, but laced with those heavier elements, the carbon, the oxygen, the iron, that were forged in the hearts of previous generations of stars and scattered through space. The star itself is a child of the stardust, and the disk of material swirling around it, the disk from which planets will coalesce, is also rich in these same elements. Rocky planets like Earth can form, composed of silicon, oxygen, iron, magnesium. Oceans of water, containing oxygen forged in a star, can pool on their surfaces. Atmospheres rich in nitrogen and oxygen can develop. And perhaps, on some of these new worlds, formed from the ashes of the old, those elements, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, might combine in even more complex ways, stirred by the energy of their young star, perhaps giving rise to life itself. The very atoms that make up our planet, the air we breathe, the water we drink, and indeed, our own bodies, were created long ago inside stars that lived and died before our sun even existed. We are, quite literally, made of stardust. This is the great cosmic cycle, playing out over and over again across billions of years and throughout the vast expanse of the universe. Stars are born from clouds of gas and dust. They live their lives, fusing lighter elements into heavier ones within their cores. They die, returning much of that enriched material back into space. This material drifts, mixes, cools, and eventually gathers under gravity's patient hand to form new clouds, new stars, new planets, and potentially new life. It is a cycle of creation born from destruction, a continuous process of cosmic recycling. The end of one star's story is merely the prelude to countless new beginnings. The stardust dreams of the universe are dreams of perpetual renewal, whispered across the ages in the silent, drifting clouds between the stars, waiting to awaken into light once more. And as you look up at the night sky, at the distant, glittering points of light, remember that you are looking at both the ancestors and the potential descendants of our own world, all woven from the same ancient, starlit thread.